Good morning everyone, my name is Danilo Comminiello, I'm from Sapienza University of Rome. The work I'm going to introduce is entitled Differentiable Branching in Deep Networks for Fast Inference, and it is authored by Simone Scardapane, myself, Michele Scarpiniti, Enzo Baccarelli and Aurelio Uncini. In this work we deal with the design of deep neural networks involving multiple auxiliary classifiers departing from the main backbone network. The auxiliary classifiers can be used to perform early exit from the networks at various layers. This makes the designed neural networks convenient for energy-constrained applications such as IoT or fog computing. First, we introduce the concept of early exits in deep networks. The early exit strategy is a rather easy concept to be understood, but it is very effective and useful for a variety of applications. An early exit is nothing but an intermediate classification step inside a classical neural network architecture. Deep networks can represent very expressive boundaries between classes. However, in many applications, much of the data can be properly classified with even the simplest classification boundaries. Now the question is, why do we need early exits? Early exits can be actually used for a variety of reasons. We are particularly interested in performing fast inference when an input exits early on and in distributing computation on multiple tiers. Here is an example of a distributed implementation of a multi-exit neural network on separate tiers of a distributed computing platform such as mobile tier or a cloud one. Designing an optimized early exit strategy is a difficult task, in particular where many early exits can be implemented. Simple strategies generally require a large amount of manual fine-tuning and are not scalable. In this work, we propose to optimize end-to-end the entire decision process, including the early exit strategy. To this end, we approximate each auxiliary classifier with a differentiable soft conditional version. Now we describe how to choose which branch to use even when a large number of auxiliary classifiers is considered. To this end, we need to reformulate the early exit strategy in a differentiable form and devise a proper training for the branches. The scheme of the proposed soft conditional output is represented in this figure, in which red blocks represent the main network, while the blue block is the additional auxiliary classifier. It is worth noting that the definition is recursive. The overall output of the network can be computed recursively starting from the first branch. Let us consider a neural network and assume that it is endowed with a set of auxiliary branches, so a set of intermediate classification branches departing from the main backbone network. Any of these branches can classify the input pattern with varying accuracy. Each auxiliary classifier is equipped with an additional early stopping decision mechanism which implements the logic to decide whether to early exit or not. In practice, GB of X and FB of X can be two outputs of a single auxiliary network sharing a common processing part. To make training differentiable, we propose to use the new auxiliary classifier as a gate to define a new soft conditional output for the branch, which is represented in this equation. The base case of the recursion is the final auxiliary classifier, in which the confidence is always set to 1. Instead of training on a sum of branch losses as classic multi-branch neural networks, we jointly train all branches by exploiting a cross-entropy loss on the last soft conditional output. During the inference phase, we can use the network in two ways. If no early stopping is needed, the recursive output provides a simple way of exploiting adaptively all auxiliary outputs like an ensemble technique. The second strategy is to consider the auxiliary values as a standard binary classifiers to take an early exit decision. Our goal now is to make the proposed training of the multi-branch logic energy efficient. To this end, suppose that exit at one branch has a certain computational complexity gamma. We would like to minimize the average computational cost of the network, in which the average computational cost of the soft conditional output is computed recursively and approximates the average computational cost of the binary functions which are not differentiable. We evaluate the proposed method on 3 different datasets with various multi-branch architectures of increasing complexity. The 3 datasets are the standard CIFAR10 and CIFAR100 benchmarks for image recognition and the recently proposed Scenic 10 dataset, which is a more challenging version of the CIFAR10. Concerning the 3 architectures, we consider AlexNet, VGG13 and ResNet18 by properly rescaling the initial layer of the network to handle the same image size. For each experiment, we train the baseline model with no branches. For comparison, we train the architectures according to the branchinet architecture, which minimizes the sum of all auxiliary losses. For the version with multiple branches, we add one auxiliary classifier after each convolutive block. Results in the table point out that having auxiliary classifiers significantly improves the accuracy with respect to previous literature. The improvement is more evident when using our proposed soft conditional approach, having higher accuracy across all datasets and architecture that we evaluated. We also evaluate the multi-branch strategy for energy-efficient inference. To do this, we simply threshold each classifier to 0.5 to decide whether to use the auxiliary classification. We report the results only for the CIFAR10 dataset, but we achieve similar results in conclusion also for other datasets. We measure the average test accuracy that we obtain, the inference time, the speed up with respect to the baseline network, and the percentage of patterns exiting at the various branches. We can see that the accuracy of the final classifier is only slightly inferior than the previous table, but always better than the other models. However, we obtain a speed up in inference time going from 12% from the simple AlexNet architecture to more than 1/2 for the more sophisticated ResNet18. For completeness, we report the distribution of the early exit confidence for 3 branches for the trained ResNet18 architecture on CIFAR10. To conclude, we propose a new formulation for networks having multiple auxiliary classifiers that can be trained end-to-end with the main backbone network. We also proposed a novel regularization term to trade off accuracy and computational cost of inference. We plan on further exploiting the differentiability of our formulation by investigating on additional regularization terms and loss functions. We will also take into account other complex network and different benchmarks. Thank you for your attention.